A student investigates the reactions of two weak monobasic acids, 2-hydroxypropanoic acid, CH3CHOHCOOH, and butanoic acid, CH3CH2CH2COOH. Part A. The student wants to prepare a standard solution of 2-hydroxypropanoic acid that has a pH of 2.19. Plan how the student could prepare 250 centimeters cubed of this standard solution from solid 2-hydroxypropanoic acid. In your answer, you should provide detail of the practical procedure that would be carried out, including appropriate quantities and necessary calculations. The Ka for 2-hydroxypropanoic acid is 1.38 times 10 to the negative 4 moles per decimeter cubed at 25 degrees Celsius. So firstly, on the side, I've written a little abbreviation we're going to use just to clear up and tidy up our working out throughout. So firstly, we want to work out the concentration of A, and we're going to do this by H plus squared divided by Ka. That's the equation we're going to be using, but we're also going to be using the equation of H plus is equal to 10 to the minus pH. So what we can do is 10 to the minus 2.19, and this is going to be squared, and then divided by 1.38 times 10 to the minus 4, which is our Ka value for 2-hydroxypropanoic acid at 25 degrees Celsius. So that's going to give us our concentration of 2-hydroxypropanoic acid, which equals 0.0302 moles per decimeter cubed. And now we're going to use the equation triangle of moles divided by volume times concentration. And that's going to give us the moles of A, or the moles of 2-hydroxypropanoic acid. So we're going to do 0.0302 times 250 times 10 to the negative 3, because we're converting centimeters cubed into decimeters cubed, and that equals 0.0755 moles of A. And then we can use our other equation triangle, which is mass divided by relative formula mass times moles. And we're going to use this to work out the mass of A. So that's going to be 0.0755 times 90. 90 is the relative formula mass of 2-hydroxypropanoic acid, and it equals 6.80 grams of A. And now we need to talk about our method. So this part of the question where we're describing the method is just asking us to explain how you make a standard solution. So firstly, when making a standard solution, you dissolve your solid in less than 250 centimeters cubed of distilled water in a beaker, but we need to specify the mass of the solid we're using. So we're dissolving 6.80 grams of solid in less than 250 centimeters cubed of distilled water in a beaker. Then we're going to transfer the solution to a 250 centimeter cubed volumetric flask. And we need to ensure that the solution is all washed out of the beaker to make sure that the mass, or all of the 6.80 grams of solid, all of that is washed out and is in our solution. Then the final step to make a standard solution is that you need to make up the 250 centimeter cubed mark with distilled water. So that's making sure that the meniscus is lying on the little, it's usually a red line on the volumetric flask, so making sure that the distilled water is up to there, and then you put your lid on and you ensure thorough mixing by inverting the volumetric flask several times before finishing your standard solution and using it. To get the marks for the method part of the question, I've split it up into 3 bullet points, and each bullet point is a mark for this part of the question. So that'll get you 3 marks. Then you get a mark for working out the concentration of A, the moles of A, and the mass of A. Part B. 2-hydroxypropanoic acid is a slightly stronger acid than butanoic acid. The two acids are mixed together and an acid-base equilibrium is set up. Suggest the equilibrium equation and identify the conjugate acid-base pairs. Because 2-hydroxypropanoic acid is the stronger acid, it's going to make a conjugate base of CH3, CH, OH, COO minus. And then because butanoic acid is the base in this situation, it's going to make a conjugate acid of CH3, CH2, CH2, COOH2 plus. We can then label the acid-base pairs. So we have acid 1 and base 1, and then base 2, acid 2. To get the 2 marks for this question, you must have the correct equilibrium written, and then you need to correctly identify the acid-base pairs. Part C. To prepare a buffer solution 75 centimeters cubed of 0.22 moles per decimeter cubed butanoic acid is reacted with 50 centimeters cubed of 0.185 moles per decimeter cubed sodium hydroxide. The Ka for butanoic acid is 1.5 times 10 to the negative 5 moles per decimeter cubed at 25 degrees Celsius. Part 1. Calculate the pH of 0.185 moles per decimeter cubed sodium hydroxide at 25 degrees Celsius. Give your answer to 2 decimal places. The equation we're going to use is POH plus pH equals 14 and POH equals minus log 10 of the OH concentration, or OH minus concentration. So what we're going to do is work out POH, which is minus log 10 of 0.185, and that equals 0.73. And then we can work out pH by doing 14 minus 0.73, and that equals 13.27, giving our answer to 2 decimal places. So if we then write 13.27 on the answer line. To get the 2 marks for this question, you get 1 mark for your working out, and then you get 1 mark for your correct answer, which is given to 2 decimal places. Part 2. Calculate the pH of the buffer solution at 25 degrees Celsius. Give your answer to 2 decimal places and show all your working. So what I've done in the top right is I've written the information from part 1 that we're going to use in this question. The first thing we're going to do is work out the moles of sodium hydroxide and butanoic acid so that we can work out the moles of the buffer. And we're going to use the equation of moles equals volume times concentration. So for sodium hydroxide, that's going to be 50 times 10 to the negative 3 times 0.185, and that equals 9.25 times 10 to the negative 3 moles. Then for butanoic acid, we're going to do the same thing but with different numbers. So we're going to have its volume of 75, then timesing by 10 to the negative 3 to convert centimeters cubed into decimeters cubed, and then multiply by 0.22. And that equals 0.0165 moles. So then if we work out the moles of the buffer, we need to minus these 2 values. So it's going to be 0.0165 165 minus 9.25 times 10 to the negative 3, and that equals 7.25 times 10 to the negative 3 moles. And we need to then work out the new concentrations for the buffer and sodium hydroxide, because we're going to be using the equation of Ka equals concentration of H plus times the concentration of A minus divided by the concentration of HA. So the concentration of HA, that's our buffer, so that's HA, and A minus is NaOH, so we need to work out their respective concentrations in the total volume of 125 centimetres cubed. So for NaOH, that's going to be 9.25 times 10 to the negative 3 divided by 125 times 10 to the negative 3. We're using the same equation triangle as we did for part 1, and that's going to equal 0.074 moles per decimeter cubed. So that's its new concentration in the buffer. And then for the buffer, we've got its moles, so we're going to do 7.25 times 10 to the negative 3 divided by 125 times 10 to the negative 3, and that equals 0.058 moles per decimeter cubed. So now we're using our second equation, and we're going to rearrange this equation. So we're going to rearrange so that we have H plus, or the concentration of H plus, as our value, and that's going to equal Ka times HA, or the concentration of HA, divided by the concentration of A minus. So plugging in our values, we're going to have the concentration of H plus is equal to 1.5 times 10 to the negative 5 multiplied by 0.058 divided by 0.074, and that equals 1.176 moles per decimeter cubed. And then finally we're going to use the equation for pH, which we used in part 1 of this question, so the previous page, and that is pH equals minus log 10 of the concentration of H plus. But in the other part we used concentration of OH minus, and it was POH. But the equation still works for pH and POH. So for pH, this is going to be minus log 10 of our concentration of H plus, which is 1.176, and that equals 4.93 to 2 decimal places, which we can then write on the answer line. To get the 4 marks for this question, you get a mark for working out the moles of sodium hydroxide, a mark for working out the moles of the buffer solution, a mark for working out the concentration of H plus, and a mark for working out pH correctly, so 4.93.